Welcome back, everybody. We are up to lessons 12 and 13 of Unit 4. And in this lesson, we are going to introduce a new number, a new irrational number called E. You might remember from your mathematical past in a irrational number known as pi. Well, E is similar to pi, except it has a different value. We know that pi is approximately equal to 3.14. Well, as it says here, E is approximately equal to 2.718. And just like pi, we call it an irrational number. This means that it can't be represented as a fraction and the decimal is non-repeating. So think of the digits of pi. Pi goes on infinitely. It's a non-repeating decimal. You can't write it as a fraction. It's an irrational number. E is the same way, except it's just equal to a different number. Okay. The number E is used by engineers, economists, and scientists for many different mathematical models. And the reason it's called E is that it stands for Euler's number. Sometimes it's pronounced Euler, sometimes it's pronounced Euler. But that's what E stands for. And in the case of this particular unit, it's often used in cases of continuous exponential growth and decay. What do I mean by continuous exponential growth and decay? So we have talked about previously different cases of exponential growth and decay. So let's say we have a situation where the number is doubling every time. And it's doubling every 6 hours. Say we have an element that's doubling every 6 hours. It's continuously increasing. It's not that it stays at the same number for 5 hours and 59 minutes, and then at the sixth hour, it automatically doubles. And then it stays at that number for another 5 hours and 59 minutes, and then at the sixth hour doubles. It's gradually increasing over time. That's what we mean by continuous exponential growth and decay. As a result of that, we have right here an alternative exponential growth formula that utilizes the number E. So instead of A times B to the X, an alternative formula would be A times E to the power of R times X. So A, as with the other exponential growth formula, is still the initial value. Okay, E is E, and R, in this case, is the growth rate, not the growth factor. Okay, so remember, if something is going up, say, by 2% each time, the growth rate is 0.02, but the growth factor is 1.02. So there's a difference between the growth rate and the growth factor. And it works the same with exponential decay. All right, so with that in mind, we are going to take a look at the examples for this lesson. So here are some situations in which a percent change is considered to be happening continuously. Okay. For each function, identify the missing information and the missing growth rate expressed as a percentage. So identify the missing information and the missing growth rate expressed as a percentage. So number one, at time t equals 0, measured in hours, a scientist puts 50 bacteria into a gel on a dish. The bacteria are growing and the population is expected to show exponential growth. So this is our function. Okay, notice 50 is the initial value. Okay, E, and then remember it's R times X. In this case, they're using T instead of X. But this 0.25 right here is going to be the R value, which if we go back to our lesson notes, the R value is the growth rate. So 0.25 is 25%. So the continuous growth rate is 25% per hour. So it's growing at a rate of 25% per hour. Okay. Number two, in 1964, the population of the United States was growing at a rate of 1.4% annually. Notice that's my continuous growth rate per year, 1.4%. That year, the population was approximately 192 million. The model predicts the population in millions T years after 1964. So again, remember our formula is A times E to the power of R times X. So my A value is my initial value. What's my initial value here? It's 192 million. So I'm going to put in 192 with the understanding that that doesn't mean 192 people. It means 192 million people. Okay, so A times E to the R times X. In this case, they're using T again instead of X. Well, if my continuous growth rate is 1.4% as a decimal, that's going to be 0.014. So my function is 192 times E to the power of 0.014 times T. Okay. So that's number two. Number three, in 1955, the world population was about 2.5 billion and growing. The model predicts the population in billions T years after 1955. Okay. So again, my initial value in this case is going to be, I'm going to put in 2.5 with the understanding that that means 2.5 billion. Okay. And then right here is my growth rate, 0.0168. Okay. So as a percentage, that's going to be 1.68%. So my growth rate is 1.68% per year. 1.68% per year. Okay, so again, to reiterate, in this lesson, we're introducing the number E, and then we're using that number E to use an alternative exponential growth formula that's different from the formula that we used at the very end of last semester. Okay, that is it for lessons 12 and 13.